So before we get started, who are we? Uh, we are Voxel51. We are the lead maintainers of the open source tool FiftyOne, as well as the enterprise tool FiftyOne Enterprise. We'll be looking at both of these today. If you don't know what a voxel is to a video, what a pixel is to an image. It's that volume element. And if you don't know what the story is behind FiftyOne, FiftyOne started way back when, about 7, 8 years ago, spun out of the University of Michigan from a professor-student combo. The joke goes all the way back that there's two stories. One that all the cool future tech of the world, all the AI will be built in cool secret labs. So one of our co-founders wanted to name it after Area 51. The other one said, well, no, I really just had 50 bad ideas, and then I had 51. You choose your own adventure there on which one you want to subscribe to. But my name's Dan. I'm an ML engineer and developer evangelist here at Voxel51. I've been working in all things physical AI for about a year or two now, really diving myself deep and kind of watching this field and sector of AI explode recently. And I'm happy to bring you both the latest and greatest in physical AI today, as well as how you can get started with the Physical AI Workbench from Voxel51. However, let's start first with what is physical AI? Why do we have another buzzword? What does this all mean? So if you're not quite up to date about what physical AI is, let me help break it down from you. And I have this nice little graph here from Jensen that will help kind of break it down, the major steps of how we got here. So going all the way back to AlexNet, we think of ImageNet competitions, the first CNN. The main problem that we were tasked with solving back then was, is this a dog or is this a cat? I give you a JPEG. Is this a dog or is this a cat? This kind of, obviously advanced, but, at the time it was still very basic, right? I'm going to get a media file and I'm going to make a prediction on it. Of course, over time, we got better at this. We moved to things like detection and segmentation. It doesn't have to be a cat or a dog. It can be skin cancer. It can be X-rays. It can be, even videos and things like that. And obviously, we moved into NLP and all this kind of stuff. So we got better and better at classifying and detecting and segmenting things. And then eventually, obviously, big boom around 2022, 2021 with ChatGPT comes out. Everything changes. These models are getting humongous. They're giant, giant, giant. GPU budgets are going through the world. Data sizes are going through the world. And now we can begin to ask to create things, right? I'm not going to dive into the world of LLMs today, but the idea that I want to bring home here is that I'm asking to create things, right? We're generating new content. Sure enough, this leads into agentic AI, which is kind of where we are now, and moving forward towards physical AI, which is, well, if I can create things, I can create code. And if I can create code, I can ask it to do tasks for me, right? And, basically look at pieces of code or look at existing content and then take an action on it. This kind of has now gone into a new type of idea. When we look at specifically how it relates to vision, what we call a vision language action model, or VLA. And this sits in between agentic and physical AI, where I'll give you a very classical example here, which is I'm going to ask my favorite agent or ChatGPT or Claude or whoever you like. I'm going to ask it to go buy me a new jacket. And I tell it I want a red jacket. It needs to keep me warm in the winter. It just got really cold here in New York City with all the snow. And I'm going to ask it to go buy me a red jacket. Now, not only is it going to scrape all the information it knows on the internet for where to get jackets and what's the best deal, but it might remember things from my past conversations, such as, well, I know Dan's a large, so I got to make sure that the large is in stock. And, he asked for a red jacket, but he also likes the color orange. Maybe I'll include some of those. Well, what we're seeing here is that this has been very successful in a lot of places in AI. But in that example, we're still not really getting over this traditional JPEG or just kind of reading the media file, right? It's a lot of media files, text, JPEGs, things like that. And then I'm taking actions based on what I see in this environment. The main difference for physical AI and why this is a whole new really era that we're ushering in for AI is because it's no longer just looking at like a raw media. It's not just JPEG or an MP4 or JSON or text or something like that. It is encapsulating the physical world into a digital context. And when we think about this, physical AI is all about robotics and autonomous vehicles and drones and automated agriculture machines and mining and all these really great use cases that are out there where it's not enough to just JPEG it out, right? We are taking in motors, velocity, poses, GPS coordinates. We might have 6, 7, 8 different sensors, LiDAR sensors, radar sensors, and all these other different factors that are happening in the environment around the robot or the physical AI agent here, where it is a huge step change. So the data complexity, the model complexity is so much different than where it was before, where we really need to now rethink and reconsider exactly how we're building our entire data pipelines. It really is beginning to feel a lot like kind of when detection and segmentation really began to take off about a decade ago, where it's just all these new types and all these new methods and all this stuff that's going into it, where we don't want to make the sins of the past, right? Where it's really going to come down to how best can we encapsulate the data and do that physical to digital translation. How did we get here though? Why are we diving into this space in the first place? It's not like self-driving cars haven't existed. Some of you guys might have taken a Waymo this week or something like that, right? So why are we getting to this space, right? Well, the key theme here is that 97% is not enough, right? And I arbitrarily choose this number because any given autonomous vehicle is probably around 97% right most of the time. You might be somewhere between 90, and even Waymo might be 99% or something like that. Tesla, pick your favorite. But it's not enough, right? If it was enough, it would be everywhere. I could walk down the street and buy an autonomous vehicle, get into it, take a nap, and my car would drive me around. And it wouldn't be a concern, right? But we're not there. And why aren't we there? Well, it turns out that a lot of the problems that we're seeing cannot be described and solved based on the systems that we're currently deploying, right? To dumb it back down again, it's a lot of look at a JPEG, look at the street ahead of me, identify what the hazards might be, and then take corrective actions, right? So it might say, look at pothole, dodge the pothole. But this isn't enough to do, right? Because we get into this really long tail distribution problems of like, hey, is it worth to dodge the pothole if it's going to make me like swerve into oncoming traffic? How big is this pothole? Do I treat all potholes the same? Some potholes are good and some potholes are bad, right? And I need to know what happens when I hit that pothole. How bad is it going to be? And how can I keep the driver and the drivers around me as safe as possible? And this is exactly where we're seeing this complete change, right? Some examples that I can go through as well that are similarly like this is aggressive drivers, right? When do I make my self-driving car take an illegal action for the safety of the driver? Something that might come up is something like a driver coming down the wrong side of the road. I'm going to swerve away from him, and that's the safety action, but I'm teaching the car to break the law. Is that okay? Another one is tires. We look at tires all the time. We see 4 tires on every car almost, right? And so how do I teach a AI model, hey, tire that's not attached to the car, that is rolling right at you, that's a bad tire. And we need to dodge those tires away from it, right? I can go on and on of things like jaywalkers, adverse weather conditions are very difficult, as well as trying to transfer this knowledge to different regions. I have a Korean toll booth here with blue lines and arrows and language in different spots where if I trained my car on San Francisco, it's not going to be able to just drop into Korea and work perfectly. And so what we're going from here is a whole new kind of way of solving this problem, which is we are going beyond next token prediction, right? We think about the world of LLMs and ChatGPT. I ask it a sequence of words, it gives me a sequence of answers back, right? This is not going to work. We've, I think, fully decided across the autonomous vehicle field, as well as other physical AI fields, this is not going to work, right? And the reason why it's not going to work is we can't keep on just predicting one token at a time when there's a whole state of an environment around you, right? We need to be continuously monitoring the state, continuously updating it, continuously understanding the changes. That way we can have the foresight to plan what our next move might be. So instead of going from words, we're going to worlds, right? And this is the idea of building world models and understanding state dynamics. If I drop a ball, can I have a model predict how much of that ball is going to bounce, right? We don't have all this solved today, but this is exactly where the field is going. And this is why you see people like Yann LeCun, Fei-Fei Li, all these other people leave their traditional posts and start building these world model AI companies, because this is going to be, in all beliefs right now, the next generation of what's going to be the knowledge dump of AI. And it's really exciting to be at the center of that. I'm going to answer a question real quick before we move on from one of our friends here. Clarifying physical to digital translation. What do we mean by that? We mean literally like that. I don't want to define it too much, right? I'm going to tell you how we do it today. But the whole idea is if you are trying to train a model to predict the world, everything around you, from how the raindrops fall, from how two cars that run into each other will react, to all these different number of things and elements, right? There's probably infinite amount of things. How best can we translate from that physical world to that digital world so that way I can train a model on the digital and then eventually deploy it back to the physical, right? So I'm going to leave it specifically loose for you, right? We're going to talk about how we do this with robotics and autonomous vehicles today, with velocity and poses and all this kind of stuff. But it can be a very, very deep well that we're getting into here over the next years or two, with density and material structure and all these kind of things that are going to potentially come up in the future, right? And it's all happening right now in the world of simulation and this kind of physical to digital pipeline that we're building here. But great question. I'm glad you asked it so I could specify. One more thing before we move on. So it seems like LLMs are a dead end if they're built for predicting next token. It's not that they're a dead end. They're going to have their uses. Agents are great and everything like that. It's just we need to take the next step, right? We can't pass in perception use cases to an LLM and hope for the best, right? We need to give the LLM or this large model, whatever we're going to call it in the future, world models, all the idea of how the real world works, as some of our friends mentioned. Like physics and states and context, and being able to not kind of have this hindsight reasoning where it's kind of over correcting to make you happy, right? I don't care. The car has to drive. Don't make me happy, right? The car needs to be safe. We need to have all these long tail distributions problems solved. That way, when the unimaginable, the unpredictable happens, the car is still going to be accurately able to take the right prediction because it's not fully relying on everything it's seen, right? It's able to make these predictions of what might happen next. All right, moving on. I might have seen this slide before because now more than ever, it's ringing true, where the villain of ML is consistently going to be bad data, right? Models are going to change, GPUs are going to get better, but your data is always going to be your data. And now that we're deploying these things into the real world, such as these cars and these drones, these robotics, you're getting more and more model bias issues, right? We cannot have this happen, right? This can lead to lethal physical danger. Just because you're in a neighborhood that looks different, just because someone is wearing clothing that looks different, does not mean our car can make a different prediction, right? On top of this, outside of bias issues, we're sitting on hundreds of millions of hours of drives across the world, right? We're talking about the world's amount of self-driving data and robotics data alike is in the, thousands of petabytes at this point. So surely within these thousands of petabytes, there's corrupted data, miscalibrated data, failing hardware, lag, just poor, shitty quality data that we can't be training on. We're training so much, we're training so often that we cannot afford to give it poor data. We need to make sure that if we're really trying to match this physical to digital translation, that all the data going in is as high quality as possible. And then it seems like most of the teams are spending all their time here, right? I talked to engineers across all the tier ones. I've talked to engineers from Waymo. I've talked to engineers from Wave. I've talked to every other kind of car manufacturer, robotics teams out there. Data consistently is one of the major problems. And even after doing all their data pipelines that happen today, it seems that still 50% of their simulations or physical AI pipelines are failing because of poor calibrated data or poor data quality. And this problem is really starting to accrue as we move into more complex physical AI pipelines and data structures and workflows, where we're burning resources at both ends of the spectrum. One is the synthetic data jobs are consistently failing because the calibration is off, or because the data input is wrong, or the transformations are off, right? The other part of it is the moment the data comes off an AV or a robot, I'm going to mention AV or robot, and all my examples today are autonomous vehicles. Just know that they're interchangeable in the world of physical AI. It's images, it's LiDAR, it's radar, it's perception. What you use it for doesn't make a difference, right? So, if you're in a robotics field, don't feel like it doesn't work for you or anything like that. And if I keep on mentioning AV, it's just because the one I'm the most familiar with. But when the data comes off this autonomous vehicle, it instantly gets siloed, right? Which means if you're the cruise control team and your buddy's on the self-parking team, both of you heavily relied on like radar and perception for the application you're building here today. But you don't actually use all the different teams, right? For instance, like cruise control doesn't care about the car behind you. I only care about the car in front of me. So I only use the radar from the front of the car. But parking, I need both sides if I'm like parallel parking or something like that. So if I created this great new like radar model or something like that, for instance, I can't share it with my other team member because he has a separate data pipeline and another person has a separate data pipeline, and every team has their own data pipeline. And so it makes it very hard to not only share internally, but as well as grab the greatest and latest models externally to build into your stack. This webinar will be shared to everyone to view as later. It will be emailed to you afterwards as well. So how do we fix this problem? This is where we have developed the Physical AI Workbench for you, a new product coming from Voxel51. This helps you don't get stuck in notebooks. It helps you confirm your data set is calibrated with a number of different checks that we're going to talk about, right? So getting out of this notebook, getting away from your friends sending you zip files and using, test.ipynb for our latest, quality check. We need to deploy this at scale. We need to do it at a very, very large scale and make it so everyone in our organization can access it easily. So what is the Physical AI Workbench? Let's kind of start there. Well, when you audit your data and you build it all in, it helps you generate lifelike digital twins through NVIDIA Omniverse like this, right? Where we can see real data coming off the top and then synthetic data, NuRec on the bottom, doing a 3D reconstruction in this case. It also helps you pipe to multiple different workflows after you have that audited data set. So we audit your data set over 100 of different checks. We load in all that context for that physical environment, and then confirm and give you confidence that whenever you expand to physical AI workflows downstream, such as reconstruction, the Cosmos models, as we'll look at in a second here, or your own physical AI model training, that you have confidence that the scenes that you're training on are well calibrated. This helps get your data production ready, where no more expensive training runs fail. You can be confident that before you go spin up that H100 or H200 or whatever it might be, that your model's actually going to train and succeed, as well as no more model input mismatches. I'm sure if you're experienced in the field, being able to export from one dataset format to another dataset format, or just expressing your dataset in a way that a specific model wants is very, very difficult. All of that is handled within the Physical AI Workbench with many different built-in transformations, as well as supporting some of the best models out there today. Then lastly, we are by no means a physical model company ourselves, right? There's many out there. NVIDIA provides a bunch. There's open source ones from NVIDIA and others, as well as other ones that I'm sure will pop up in the future as well. FiftyOne is committed to being the platform where you can compare and evaluate all these different options in one tool. So there's no more apples to apples to oranges or something like that. When you compare the different reconstructions or compare the different models inside of FiftyOne, you're always going to understand which one is better for your data. On top of that, because Physical AI Workbench is built with FiftyOne Enterprise, you get to democratize all of your data. It's more than just an audit. It helps you create rich data pipelines for your whole organization that instantly let you transfer to any other coordinate convention. This allows for rapid sharing across any of your teams, any new innovations, any new model trainings, anything like that. You can now share across your entire organization, allowing them to get access to that data lake of all the rich, pre-audited data sets to then pull in for the specific task using a number of different curation methods that we'll cover towards the end here to help really bolster your data pipeline and data infrastructure. We also help fill in your gaps with enrich options. We'll be covering this later as well, where Physical AI Workbench doesn't just ingest your data set. It doesn't just audit your data set. It can help find the gaps in your data set and what data is missing and actually automatically fill it in for you. That way you're always getting that best model results down the stream. Lastly, you don't want to risk your most valuable resource. And I'm going to pause a little bit here so we can understand uh, exactly what I'm trying to get across here is unlike the past with, the JPEG models and things like that, there wasn't really a lot of room for things to go wrong, right? It's either the JPEG was there with the label or it wasn't, right? And sometimes the labels were wrong and things like that, and we developed tools to fix it. Uh, Now we're doing that same problem. It's just 100 times more complicated, right? So, audit isn't the sexiest word. We're going to look at a lot of non-sexy things here, and I promise I'm going to try to get through it as fast as possible and without being super boring. But auditing is so, 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 so important in the world of physical AI. And ask any of the top engineers and they'll agree. Where if you don't believe in auditing, like why even check, right? The sensors were calibrated when the car left the station, right? Or, we have plenty of drives that seem to have been doing well so far. It's not like we haven't been able to train any models up until today. We've already caught mistakes up to $50 million using Physical AI Workbench, right? Where data sets that were collected for years, and were paid a lot of money to collect and annotate and, store are just broken. Like there's completely garbage, right? Like the sensors coming off of it are not reporting the correct information. So pose is all over the place. You just have a number of missing crucial timestamp information that wasn't captured at the time of collection, which now renders in the modern physical AI world this data set useless. I mean, like petabytes, useless. And so don't be the person that is making these $1 million mistakes, right? Models will keep on changing. GPUs are going to get better, but your data is always going to be yours. So it is very, very important that you protect it. Everything here, as I mentioned, is built on FiftyOne Enterprise. So you're always going to have an ability to directly connect to your cloud and load this all in at a browser. We'll probably take some looks at this later. But this gives you a unified view of multimodal data from images, LiDAR, radar, and more. Everything is queryable, curatable, filter, sliceable. You have a field on your data set. We can help sort and slice and filter and search on your data set for that field. All the immediate data integrity checks that go into it as all in one shareable, reproducible workspace. For a quick overview of our physical AI workbench, this is what it looks like. We're going to come back and reference this a couple times throughout our slides here. But your AV dataset or your physical AI dataset we're ingesting in here. From there, there's some kind of inspection and curation you can do yourself. But really where it all starts is when we begin auditing this dataset to check that everything that we ingested is correct and in its right place, well typed, well formed. Everything is calibrated. We run a number of different photogrammetry checks on it. We do many mathematical calibration checks, as well as some LiDAR projection and additional checks on top of this to ensure that all the physical AI context is as concrete as possible. We then help enrich your data set by adding in additional information, helping you with things like verified auto labeling if you're interested, embedding searches, as well as QA annotation using models as well the neural reconstruction and Cosmos transfer paths, which are highly recommended and useful today, which a lot of our physical AI customers are leveraging inside of their workflows today. Using neural reconstruction, you can do a lot of awesome things, such as generating new novel views, as well as with Cosmos transfer, you can augment those to have new kind of environmental changes. You can even change locations using the transfer model. I'm going to pause real quick to answer some of our questions that are coming through here. Thank you, chat, for kind of being so active. I love this. This is great. So some friends ask about NuRec being supported on the RTX 50 series. You're going to have to need about 40 gigabytes for NuRec today on most driving scenes of around 20 gigs or so. So that's 40 gigabytes is like an A100 or so. They're going to drop this down in the future, I've been told, and they're doing really, really great work doing so. But just calling that out now that it takes about that much to generate the best reconstruction possible. And that's because there's so much more than just a naive Gaussian splatting that's happening during that. The last one is, how do you modify the NuRec models in your pipeline? And can you extract semantic information, physical properties like geometric structures and depth from NuRec? These are great questions. We're going to answer them later on, I believe. The answer in short is yes, but the actual answer is much longer than that. So I'm going to leave that there. All right, moving on. We're going to talk about some of our data here and in getting ready to ingest. So when we talk about physical AI datasets, what are we talking about today, right? We mentioned all the things that you can potentially grow towards and we can grow as a field towards. But today, this is kind of what we're looking at here, where when it comes time for metadata outside of raw media and things like that, we're going to look at things like the timestamps. There's a bunch of different timestamps we'll go over. Camera intrinsic, shutter, labels, everything like that for on the camera side, as well as for the LiDAR. We're asking for both labels as well as a LiDAR point cloud information such as intensity, elongation, point timestamps, inclinations, azimuths, and much, much more. After you have all this built in, we then audit on all the ones that you do have. You don't have to have every single one. We'll touch that in a second. But once you have it all in, it's audited, it's checked, it's confirmed, and anything that is flagged as potentially an issue will be raised to you. Then from there, you can generate with NuRec, create these new novel views, QA sensor placement, as well as leverage things like the asset harvester to actually pull out the cars from the scene, as well as things like use the NuRec fixer to generate even higher res video than a normal Gaussian splat. If you want an example of some sensor placement, here's an older example here where I can kind of move my car around. And in this tool, you can kind of play around to see where you might get different results if you move your camera around. This kind of buffering is just a factor of Nerf Studio in this case. Everything that is getting rendered for your new novel views is accessible through an API using a gRPC connection to the NuRec tool. You can also augment your scenes with Cosmos transfer. So in this case, we can take in that scene and make it rainy. You can even see all the drifting of the rain behind. Or if you want to be crazy, you can make it a sandstorm earthquake as well. It's really up to your imagination. But Cosmos transfer is going to maintain all that structure for you as you kind of push it through. You can also leverage the Cosmos embed model. This is a video embedding model trained and fine-tuned on physical AI datasets to help find complex behaviors using video embeddings, such as cut-ins, intersections, right turns, left turns, things like that, and help you visualize the distribution of your and coverage of your dataset using the embedding visualization of FiftyOne as well. That's our kind of highlight of everything that we're going to be covering today and all the opportunities here. We're going to hop into getting started with loading our data. This is a very long process that I'm going to jump through because there's a lot of different things you can imagine that we're going to cover for physical AI. However, always feel free whenever you watch this video back in the recording to kind of reference this. This is where we're always going to be starting. And right now we're looking at this top path here. And we're going to be using all that metadata that we were just talking about before. So let's start talking about what's required. I'm going to give you some helpful resources in a second here to always come back to. Once again, this is going to be recorded, so don't feel like you need to have every single one of these memorized today. But just calling it out that there's going to be plenty of options for us. So what is required? We're definitely going to need the timestamp, at least of the frame. We're also going to need the intrinsics of the camera. We're going to need the poses, both the T-rig world, that's from the car to the world position, as well as the T-sensor rig for the sensor to rig transform, as well as our scene ID, and then any additional pose timestamps or rig timestamps if you have them, right? If you're not familiar with pose timestamp, that's kind of the timestamp coming from when the pose was captured, specifically the rig world. We're also going to need some required stuff for our camera metadata. This is going to be basically when does the camera open and close with the trigger time, the readout time, the shutter time, and the shutter type. This is how long it opens, which direction does it open, and when does it close. And then it's distortion coefficients if you have them in OpenCV order for any of your fisheye or any of those kind of specific cameras that you might have. If it's undistorted, that's fine as well. For our LiDAR, we're going to have a lot here. Inclination, azimuth, range image indices, point timestamps, our XYZ start, intensity, elongation, spin direction. There's a lot going on here. The good news is that Physical AI Workbench will handle all of this. As long as you give me a LiDAR point cloud, we can then infer all the different metadata that is needed for these complex work use cases, such as NuRec. Moving on to some of the great to haves, any annotations are great to have. Specifically, cuboids are the best to have, right? That helps bring structure to your reconstruction, as well as it helps call out what we call dynamic actors. which is all of our moving objects inside of our reconstruction, such as pedestrians or other cars. That NuRec, unlike other Gaussian splatting methods, takes additional actions to ensure that they're going to be there. Our friend in our chat asked, is there a maximum frame rate that the tool support? Does it support dynamic frame rates? Absolutely. You do not have to have like a LiDAR point cloud for every camera rate, as well as, you don't have to have, every single sensor for every single frame. You just need to be consistently not overlapping your frames, right? We need to make sure our frames are consistent. We'll see that in some of our audits later. As well as, we recommend that you keep your scenes from anywhere to 20 seconds to really you shouldn't go longer than 40 seconds, just to make sure you have kind of the best overall training process when you throw those Gaussians at them. So absolutely, we can support all the dynamic frame rates and, multiple different frame rates with it between sensors, as long as you're not leaking your timestamps. As I mentioned, that's something we can audit as well for you. Some small improvements are things like GPS, velocity is good if you're driving really fast or accelerating, decelerating very fast. Helps with some of the pose estimation. As well, if you have secondary ray bounces, this is whenever your LiDAR bounces somewhere else, and then comes back to you. We can handle all of these to make sure that you're getting the best kind of results, but they're not mandatory. They make very minor changes on how well your reconstruction and physical AI workflows today are issued, at least for reconstruction purposes and transfer and Cosmos purposes, at least. So how do we build the data pipeline? Well, datasets come in many shapes and sizes. Popular formats are like the Waymo format, the nuScenes format, and PandaSet. However, many people still have custom dataset types on top of this that they've already built and things like that. As well as when you find these dataset standards in the wild, it's actually really rare that they actually perfectly subscribe to that standard. This happens with nuScenes, for instance, all the time, where you might get different data sets that are not the original nuScenes dataset that are in nuScenes format, but are very much not in the nuScenes format, right? They diverge in some different ways and things like that. Leads to a lot of errors in traditional tooling today. However, there's no issue for the Physical AI Workbench because once the data is in FiftyOne, we're agnostic to where it came from, right? I'm testing based on the physical context you've given me, not the name of your file extensions or what folder it came from, right? We're going to walk through a couple of these examples of how to get started. I'll give you some real examples of how this is used in datasets like nuScenes, PandaSet, as well as call out some of the things that you need to be aware of. As I mentioned, this is a little in the weeds here, but I just want to make sure that we're catering to those members in our audience that have maybe never seen how to build a data pipeline for physical AI before. So we're going to do our best to make it as abridged as possible. Just know that we have a full self-paced guided tutorial in our documentation all about how to build a self-driving car dataset. This should help make your life much easier. I'm going to paste this link to the chat right now. So if you want to try practicing yourself with a little bit more of a simpler example than some of what we're going to be doing today, be sure to check out this docs. It's really, really great. It helps you get started. As well as I highly recommend that you check out our AI. I don't know why my GIF is so bad, but if you ever have a question, you can click on this Ask AI button, and it does a really, really, really good job at answering your question as best as possible. So if you ever get stuck and you say something like, how do I load in my self-driving data set? I have images and point clouds. The AI will scan every doc page that we have, every blog post we've ever written, and give you accurate code examples on how to write this back. And you could even do things like ask follow-up questions that you might have, either to make it more clarify some things that it brought up, or ask a follow-up question based on the information you just received. So I'm going to ask now, hey, can I load in radar as well? And our AI is going to answer that as well. I can personally attest to this. Adonai, my co-host here, is the brain behind the AI, but it is really, really good, especially for asking new questions, as well as even very specific questions. I actually find myself using it all the time in order to remember syntax or try to find a doc page that I'm having difficulty finding. But I highly recommend you checking that out if you want to get started a little bit easier. So, however, you have the real deal here, myself. We don't need the AI to help describe you. We don't want this whole webinar to be AI-ified, of course. So let's dive into our steps here. We're going to have a couple things that we're going to go through here. First, we're going to discover our data. Then we're going to resolve the calibration. This is our poses and such. Then we're going to align our time and timestamps. We're going to build our samples in FiftyOne. Then we're going to attach labels to those samples, and then we register the data set. These 6 steps help make up our main data ingestion pipeline, and we'll look at some very brief abridged examples on how to get through it. As I mentioned, if you are interested in trying it yourself, check out the open source guide if you want to try just your initial pattern, as well as for every single one of these that we do, we will always help support custom data sets, right? So if you're interested in trialing out Physical AI Workbench, but you're worried that your data is a little complex or messy, no worries, right? We're always happy to kind of hop on a call and demo to you and help you build through these custom data sets. We have had no issues so far kind of getting these up and running. So our first step here is just to discover our data. We're going to have some code examples on our right as we talk about it on the left. And the first thing is just loop over the structure of your data set, whatever it might be. If it's a nuScenes data set or PandaSet data set, it might come with certain dev kits and things like that. That's great. Not every data set format has a dev kit, so you have to just kind of rely on traditional folder patterns and structures and stuff like that. Either way, the first step always starts with what is actually in the data set I'm trying to load. Do you have multiple scenes? What is found in the scenes? How many sensors are in the scene? Kind of get your idea of how much data we're going to load in here. This is always great too if you want to do things like load in just one scene or something like that. And then this idea of a scene descriptor, it's just a fake class I made up, where really what we just want right now is the scene ID, where the scene is located in your directory, or wherever the samples are located at least, what sensors we're working with, and what metadata seems to be available. Once we grab all of this, this will help us then parse the rest of it downstream. For example, this is how we do it in nuScenes. We do have a dev kit in this case. So we're going to grab all the scenes from the nuScenes dev kit. I can grab the token, and this is going to give me the token for the entire scene. And then we kind of loop through all of our samples afterwards. For PandaSet, we actually have to look at the folders and identify the structure here. We do this using a function. We identify that there's 50 scenes or something like that, and then we iterate through those scenes afterwards. When we do this, we want to make sure that we're grabbing all the sensors as well as kind of creating the containers for everything that we're going to store later on. Next, we're going to resolve our calibration and make sure that everything is loaded in the way that we expect. The most important ones to cover here are camera intrinsics and distortion. We're storing these in FX/FY, CX/CY with height, your classical K, as well as for distortion is K1, K2, P1, P2, K3. We grab these, store them on for every sample we grab. So now that we're not looking at all the scenes, we're looking at each frame at this point. We want to create this function that's going to grab the poses for us. So given a specific frame and sensor, grab the intrinsics, grab the distortion, and then for every sensor, both LiDAR and for our cameras, we want to get the transformation matrices. This will be a T-sensor rig, which for most samples, it's going to be global and never changing because the rig doesn't change. But we want to make sure we store it on samples nonetheless, because you might have multiple type of vehicles on every single one of your data sets. So we want to make sure that we account for potentially different vehicles in your data set, as well as your T-rig world. This is going to be where the vehicle is in relation to the start point of the scene, right? Or the world anchor point, wherever that might be. We load these in as 4x4 SE3 matrices. If you don't have yours canonically stored in the SE3 matrices, it's in Euler or it's in quaternions, that's fine. We have plenty of tools to help convert from one to the other. When we have this, it's also a good time to mention that we have to store PCD metadata, a little bit different than the rest of it. This is just because we have all of our PCDs in one FO3 container. If you're familiar with FiftyOne, it means all of your 3D samples are in one viewer. So if you're in a specific frame and you have like 6 or 7 different point clouds or something like that, potentially, I don't want to have to look at one point cloud, then the next point cloud, then the next point cloud. I want to look at all the point clouds at once. So we just add this kind of little prefix before each one of our metadata. to kind of help identify where it's being stored. So if you're storing LiDAR pose, for instance, just know that you have to store it as like PCD underscore the name of the LiDAR, such as LiDAR top, and then the actual value that you're setting. And then our tool will then automatically help parse all of this down the way. For timestamps, let's take a breather here and kind of understand what we mean by timestamps and why is there so many different types of timestamps. Well, it all has to do with being between your clip time, right, or frame time, which is our start timestamp and then the end timestamp. If you ask me how I like to do it, your start timestamp should be the first thing, the end timestamp is obviously the last thing, and then if you look at the next frame, the end timestamp from frame 0 should be the start timestamp of frame 1, and then you kick off a whole new frame afterwards. Additionally, you have your individual frame time. This is like our master timestamp. We call this the rig timestamp, right? Now, this is more whatever you prefer, right? But the rig timestamp almost always is the start timestamp. Sometimes it's a different canonical timestamp that a person likes to store to just say like, hey, this is the centroid of my frame. You know, it could be in between start and end timestamp. That's fine as well. But the more important one is post timestamp, right? So if you have post timestamp, this is when your T-rig world was captured. This is very important because sensors fire at microsecond differences. We need to interpolate the pose to those microsecond differences in order to have the highest accuracy. Now our tool automatically does this for you, but you still need to give us that anchoring post timestamp in order to do so for you. After that, it's going to be all the trigger times, right? So for cameras, this is going to be when the camera is triggered. The shutter speed is the amount of time in between, and then the readout time. This helps us model the physics more accurately whenever we're doing things like reconstruction, as well as for LiDAR, it's going to be the timestamps of the points as we spin around. So if you have a clockwise spinning LiDAR sensor, you know, you should see as you progress around the clock, you should also, just like the clock, see those times go up as well. Everything here is going to be measured in microseconds because even microseconds of difference can make a significant difference when it comes for reconstruction, model performance, training, and all the stuff that happens downstream. Another way to kind of look at this, if it helps you break it down a little bit easier, is we're always going to have start and end on every sample. This is just the start and end of the frame. We have a master kind of canonical timestamp that we kind of refer to whenever we have just kind of I need a timestamp functions. We're always going to use the rig timestamp that comes from the LiDAR from when it starts spinning. That almost always is the start timestamp as well, but as we've mentioned earlier, you might have dynamic causes and things like that where your rig timestamp goes by the wayside. Pose timestamp is related to the pose. It's literally the T-rig world at rig timestamp. And then for your cameras, it's trigger time, shutter time, readout time, so we know exactly when it started and when it finished. As well as for our LiDAR, it's going to be when that time begins to spin, right? That scan reference time, and then each point should have a timing within that as well, right? If you don't have the specific point timestamps, it's fine. We can help build that with Physical AI Workbench as well. So how do we do this? Very easily, just write a function that references your, data frame or whatever you're storing your times in, and then just grab the correct camera name for whichever one you're pulling. So if you're pulling the front camera, pull all the times for that frame. And then for LiDAR, same idea. Grab the right LiDAR name, which is like LiDAR top or something like that for the specific frame you're on, and then grab those timings as well. You'll notice that we've kind of been collecting a lot of metadata through this process right now. It's now time to build all the samples and put them all onto one place. This is the most performant way to do it, is to do it all batched at one time instead of building each sample one by one, because this helps minimize the amount of writes we have to our database on the back end. So now that we have all of our metadata stored in these containers, we're going to start by doing two things. First is building the group. This 51 group is kind of the container that kind of represents the frame, right? So a group can hold many different samples. A sample is akin to a sensor here. So our group is going to have our front camera, our back camera, our left camera, as well as the 3D assets that we store on top of it. After we create our group, we want to store all the world context stuff that's not going to change across the frame. These are things like the position, the GPS, the velocity. These probably are only going to happen once per frame when we record. If they're per sensor, great, let's drop that back down. but any other metadata that you might have that's just, per frame, not per sensor, let's grab all that now so we're not repeatedly grabbing it. As well as we grab our master clock and we kind of create our containers for our individual sensors here. Let's start with LiDAR because it's a little bit difficult and it's a little bit harder than the camera. So we'll start there first. What we do here, we're kind of diving through a little pseudocode example here, is we want to grab our sample, get the path to where that point cloud is stored. We write the point cloud back if we need to, if it's stored in like a binary or something like that. Then we're going to grab the times that we grabbed before, add it to LiDAR info, grab the transforms we grabbed before, add it to LiDAR info. And you'll notice we create this LiDAR info container. Now, LiDAR info is our map from multiple different LiDAR point clouds to the FO3D. We then leverage this down the way to then grab the items from LiDAR info, such as the LiDAR name, the actual metadata that's stored in it, and then we store that on our FO3D. And as I mentioned, if you're not familiar, FO3D is our way to store all of your 3D assets into a single viewer, right? We don't want to be watching one point cloud and then I have to go look at a different screen to open up another point cloud. This allows you to open all of your point clouds in one place, and that way you can store it here. Cameras is much easier. Just grab all the metadata. It's super easy to write anything to a sample in FiftyOne, especially when it's a camera. Just literally call sample or cam or whatever you called your sample. In this case, I called it cam. And then just the name of the metadata field you're storing on, and then everything else. It's very easy. Just pass it in, and then I'll append that to our list at the end. Now we have all of our LiDAR samples. We have all of our point clouds. The only thing that's left to do is add labels on top of it. Any labels that you might have for cameras, this is like bounding boxes or panoptic segmentation, semantic segmentation. Load all those guys in using 51 labels. I'm not going to cover all the different types of labels right now, but I'm going to send you the doc page that does. So let me grab that for you real quick. Just know that we support all the popular physical AI computer vision labels from detections, segmentations, and much, much more, even on the 3D. But once you have all those labels on, the last but not least is putting it all together into a data set. This is going to go from sensor to group or the frame to scene. We should have all of this stored already now. We just need to add it to a data set. We take that sample container that we've been building this whole time, as you can see throughout our code blocks here. We add it to a 51 data set. We call dataset.persistent to make it true, as well as add any top-level dataset, top-level specific metadata, as well as you can create indexes to help speed up performance as well. So we can index on our scene or rig timestamp. This will make it faster whenever we curate, filter, slice, and sort on it later down the road. I know that was a lot. I purposely linked out to the example as we were getting started here, as well as promise that this is recorded for everyone, as well as I'm happy to kind of dive deep into this another time. I just wanted to get a high level about dataset ingestion so we're all on the same page here. However, if you're kind of looking like any of these people right now, because that was a headache to hear all of it, and it sounds very complex, and it's all great when it's pseudocode and an example, but in real life, it's much more messy and it's much more harder than that. No worries. This is exactly what the Physical AI Workbench is for. We don't expect everyone to do everything right on the first pass, right? In fact, as I mentioned, most physical AI pipelines in production today are broken, so it doesn't even matter, right? We're just trying to make them even better. So how do we help with this? Well, let's take an example back here. We've ingested now. Now we can start to get access to our audit and our enrich functions. So let's look at what enrichment means. Importing gets the data in, but enrichment actually makes the data useful. Every enrichment is derived. We're not adding any new sensors. Everything's grounded in real mathematics. I'm not promising 100% accuracy, but like 99% is pretty, 98% is pretty around where you would expect to find for any inferred metadata that's here. Another way to think about this is in physical AI, we can leverage many more different fields of math that we haven't explored in the past in AI, right? That you maybe are not super comfortable with, such as photogrammetry and videogrammetry and other types of geometry, where I can now leverage these complex geometries to give you new information just because you gave me 9 out of 10, right? You give me 9 out of 10 of the variables, it's now a math problem, I can give you number 10. It's not that simple though. I can actually do more than that. You give me 6 out of 10 and I can give you 10 out of 10, depending on where your gaps are and such. The idea here is that your data set, once it gets loaded into the Physical AI Workbench, isn't just as good as it was when it loaded in. It's actually better because we're filling in all the gaps and easy kind of spotting locations to get you even higher quality data set afterwards. All this is reproducible. It's mathematical. We're not diffusing these, into your data set. It's not Gen AI into your data set. And everything is audited afterwards as well to ensure, hey, everything that we created for you isn't breaking any of your pipeline as well. So for instance, we were talking about all of this headache of all these different LiDAR points you need to have and all the LiDAR metadata you need to store. This is all inferred for you, right? This is one of the best examples of enrichment where given a point cloud, I can grab all this stuff for you. You don't have to build it all yourself. We have other categories such as geometry enrichments. If you worked in Physical AI, this is a headache from transferring from FLU to FRU or any other different coordinate system. That's whenever you take your axes here, we say FLU, that's X is going front, Y is to the left, and Z is up in all the positive directions. We can now transfer you to any other of these differences and then evaluate your poses to make sure all the correct metadata gets transferred with it. It's not as simple as just transforming your point cloud. You got to transfer all your annotations. You have to transform all your sensor poses as well. But Physical AI Workbench will help you export your data set or transform your data set to any of these different ones, audit it afterwards to make sure everything is still aligned. We can also help do with point cloud enrichment, which I just mentioned, motion-aware metadata to help fill in gaps for certain things like what frames you're in, if you're in the ego frame, sensor frame, as well as some other stuff as well. We also have cross-modal enrichment for things like 3D to 2D projection of cuboids, as well as sensor alignment checks, as well as much, much more we're adding in for audit enrichment to help make the audit even better than it was before. Like I said, just harping home, this coordinate transform, it's the most popular one right now, helping you transfer between the sensor frames to rig frames to world frame, or any which way, all evaluated at specific timestamps to make sure everything's one-to-one whenever you do this. This makes it so much easier to get more and existing data sets into your workflow, as well as grab all those latest and greatest models that are expecting it to be in a specific coordinate frame or in a specific rig frame or something like that. Now you can transfer it. You don't have to rebuild your data pipeline every single time, right? You can use the exposed APIs that we provide through Physical AI Workbench to do this for you. Even these bad transforms might look believable, but you'll get terrible results downstream after a very expensive process. So we have a couple minutes here. We might go over a little bit if that's okay. But briefly, let's talk about how auditing your data set works. We have a question as we move on here. What about obscured entities? Are these backfilled? We do have some tools to help with obscured entities. There's many different ways depending on like this exact problem you're trying to get down here. For instance, like sometimes when you reconstruct, there's like a giant bust to the left of you. How do I get rid of this bust to get a better reconstruction? There's multiple different ways to help you get there. But we can track obscured entities just because they're not there. If there's annotations to go off, that definitely helps, as well as there's other techniques we can leverage to help at least spot these obscurities through some examples as well. But as we mentioned, the audit scans through, stores everything on your data set so you can filter, slice, and curate on top of your audit to make sure you're always getting to the best answer and best data set, and also spotting the issues before they actually hit training. So what does the data audit actually do? It scans your data sets for structural and temporal issues, flags the missing frames, annotation gaps, calibration inconsistencies. It validates your timestamps, your poses, your sensor alignments, and automatically scans your dataset on ingest for any of these issues that might arise. Diving through briefly some of these examples for metadata, these are going to be things like the size, the shape, and the presence. Can't tell you how many times Physical AI datasets you load in one scene, everything's there. You assume, well, the first scene worked, everything was there. You load in the second scene and not everything's there. We're missing our segmentations. We're missing our poses. Our calibrations are from the previous one and it's incorrect, right? And things like sometimes annotations are hard to come find. I don't have panoptic segmentations on every single frame of my data set, right? So what are my scenes that have the most, right? These are the answers and the questions that we're trying to have when we do our metadata check. It's also very important that we do our metadata check first as if you are expecting something to be there and it's not actually present, it's going to break all of our downstream use cases here, right? You're going to ask for your azimuth angles. Your azimuth angles don't exist. So you're going to error out. And we don't want to error out, right? We want to make sure that we're always getting positive results. And even when things don't work, we have explanations as to why. Timestamp checks. Very briefly, there's three main categories, and then how is it, way more complex than just three. But basically, the first three that you should know of: outliers. When we think of outliers, we think of, hey, frame one was at this timestamp, frame two is at this timestamp. Why was there such a big gap between the frames? We're supposed to be running at 10 FPS. This doesn't look like 10 FPS to me. It looked like it waited for, half a second or something like that. That's an outlier. Bang, we want to grab that, make sure it's out. We also sometimes see this in scene leakage. Some people reset their timestamps in between scenes. So we don't want to leak the scenes back and forth where we have too many frames, or this is from a completely different scene, or so on and so forth. Monotosity, we always need to be going forward, right? Time needs to be going forward. It sounds so dumb, guys. It sounds so dumb, but the amount of long nights I've stayed up and debugging customers' data sets and helping them understand how their time isn't going forward is one of the major and most prevalent issues you find in physical AI data sets. Because it's not just, hey, frame one happens after frame zero, and then frame two comes after that. It's, do any of your sensors ever fire before or after the next frame, right? So the last sensor of frame one cannot fire before or cannot fire after frame two starts. And this is not just between, individual frames from frame one to frame two, but it's also from, the start time of the sensor to the end time of the sensor, and the LiDAR spin and the point timestamps, right? Everything needs to be consistently bounded within the start and end timestamp of your frame. Any type of leakage can hurt downstream use cases. And in some tools and models, even equal, right? I mentioned that end timestamp being equal to the start timestamp. That in some tools will cause it to choke, right? It needs to be consistently moving forward. We help audit both for cases that are not moving forward completely, as well as are equals to each other. This helps build out a sensor hierarchy for you so you understand how, the start and end timestamp and all the other different timestamps that happen in between and in what order they tend to happen in. The last one is jitter across sensors. Everything might be staying within 10 FPS, but if you're expecting all of your sensors to exactly fire at the same time, is that actually happening? Or do we find that over time, the sensors begin to deviate over longer scenes because the timestamps are, lagging for hardware reasons or capture reasons and things like that? We also audit for that. Moving forward here, as we kind of push through calibration checks, it's all photogrammetry mathematical based for ratios, size mismatch, principal point plausibility, nan or infinite values, as well as anisotropy for calibration. As well as for intrinsics, it's determinate, nan or inf, orthonormal, and shape. So these are all, as I mentioned, calibration, mathematical, photogrammetry based, as well as we have actually in some beta versions right now, ways to do this automatically using machine learning to make sure that they're actually matching the exact scene that you're in, not just that they look like they're a correct and agreeable calibration. Next, we move on to some of the heavy hitting ones for auto project. This is going to look at your poses and do a bunch of analysis to understand, hey, this car is moving forward. We're in the right coordinate frame. We're in the ego. We're not in sensor world. It automatically detects your rig axis convention. It automatically detects your camera frame convention. And then finally does the first multimodal check here, which projects your convention onto the camera, right? This is going to be the first point most people fail because their poses are incorrect or they're not in the right ego sensor world frame across all of their sensors, right? If everything works out well, you'll get this nice clean coordinate, which is just the axis pasted onto your camera. If it works correctly, great. If not, we know exactly where to check first. It's going to be in your T sensor rigs. Something must have happened. There was an error or a mismatch. We then check that to ensure that there's no issues. And then we can move forward after the audit pass to our LiDAR projection check, which takes the next step and projects everything into the 2D. For LiDAR, paints it by depth, segmentation, or whatever other fields you might have stored on your LiDAR point cloud. And then this is the ultimate check, right? If everything is lined up correctly, if the depth matches based on what our modeling expects, the car looks aligned, the street lane is aligned, across all of your different sensors, it means you have a well-calibrated data set. Pose is being interpolated correctly. It's being transferred correctly across different cameras, whether we're pushing to the ego, the world, or the sensor, everything stays aligned. So if everything is aligned here, you now have the confidence to move forward to your next step and begin doing your physical AI workflow. All these kind of work in unison to build that best data set possible. And when you pass that data set audit, you now have easy access to all the Cosmos models, or at least almost all the models. LiDAR Gen came out like 2 weeks ago. We're trying to build it in now. It's exciting stuff for LiDAR-less reconstruction, but that will be in a future release of Physical AI Workbench. We also have easy access to the NVIDIA NuRec model. NVIDIA NuRec expects over 100 different separate inputs to the model to get the highest reconstruction. That's 100 different inputs that need to be perfectly well aligned and calibrated, no matter how many of the things you have, how many have been enriched for you, and what data you're missing, such as annotations or highly specified timestamps or whatever it might be. No matter what you have, we will always represent the best form of your data set into the NVIDIA neural reconstruction model to get the best output possible. We are now quickly becoming the premier and recommended way to get into the NVIDIA NuRec model for physical AI workflows, with us even outperforming some of the direct NVIDIA engineers because of the way that we're enriching your data set to be even better than it was when it started, right? And that's something you're only going to get inside of the physical AI workbench today. You also get all the 51 enterprise abilities, such as exporting, sharing, or collaborating with your teammates anywhere you go. The physical to digital transformation is one that you can trust in and always bank on for whatever your workflow you're building out later. This allows you to go from things like this with ghosting and kind of shitty active actor capturing and blurriness in the background to really sharp one-to-one NuRec reconstructions that are going to allow you to really speed up your simulation pipelines. Because one of the most valuable resources in simulation and AV and physical AI workflows is not money and GPUs and things like that. It's just time. How much time do I have to build out this stuff? And if I have to go test out a new camera suite or a new sensor placement, I have to then now get rainy weather and snowy weather. It's way more time consuming to go get a car on the road and test all this out and build it out. If we can model this in simulation and run the simulation faster than real time, then we're going to have much, much faster results and much, much faster model growth than we would if we had to do all of this in the physical world all the time. Through reconstruction and NuRec and synthetic data workflows, you're going to be able to rapidly increase exponentially, really, the performance of your models. However, there's more than just reconstruction you can do. We can annotate with Cosmos Reason, where you can pass in your scenes that we've been working with here, ask a prompt, such as provide a dense caption for AI training, as well as then get the outputs for reasoning, as well as that annotation that actually labels the data set with text of all the things that are happening inside the scene here. We can then use these annotations to speed up curation workflows with Cosmos Embed and Reason. So we can take the videos, whether it's a robot or whatever it is, run it through our pipeline here, annotate it with Cosmos Reason, create video and text embeddings, as well as take a Cosmos Embed model, which is lighter and trained on physical AI datasets, use that to generate embeddings, pass all that into FiftyOne, and then you can now curate based on the text embeddings, based on the Cosmos Embed embeddings, both through search, natural language, singularity search, and much, much more, really rapidly increasing your curation efforts to really help find in that petabyte of mess of all the data storage out there, those weird out of distribution, interesting scenes that we need to be training our models on to get to the best performance. If you want another example on how NuRec works, we can take existing logs, such as this recorded log data, and then reconstruct the scene with multiple modifications. So here we see the original scene, but we can have a vehicle in front now. We can delay, we can turn left, we can turn right, whatever you want you're interested in. We have many different options that we can now create once you actually have that reconstruction. And then lastly, that Cosmos transfer tool I mentioned, right, which allows you to augment your scenes from rainy data, windy data, sandstorm, earthquake data. One of the engineers I actually talked to recently that is working on workflows like this says that for every interesting scene they find, right, if I go back 2 slides here, they run this workflow to find those interesting scenes, those near misses, those cases that are 1 in a million, whatever it might be. They use this workflow to find it. They go to Cosmos transfer, and then they redo the scene 20 different times. But first, before they do that, they reconstruct it. So they actually reconstruct it, do 20 different perturbations, or they disturb it in 20 different ways. For each of those 20 different ways, they then augment 20 different times on top of that for rainy days, snowy days, foggy days, leading to 400 net new scenes, from 1 in a million to now 400 new versions of this scene to train our model on to get the best performance possible. So if you haven't seen it yet, these workflows are really redefining how we're working with visual and physical data really at all in this workflow. So the closing thoughts here, first off, don't be the one to make the $1 million mistake, right? We all are going to have budgets. We have annotation, data collection budgets, all this kind of stuff. Don't be the guy who collects all the data, annotates all the data, and it doesn't work, right? You want to be auditing right from the get-go, understanding that your data is as calibrated as possible, and that everything is as it's supposed to be, and that you can have confidence that this data that is getting audited can then be passed to all of your teams for the max efficiency and value of the investment you're putting into getting that data in the first place. The second one, physical AI is about to get really fast. I know it might seem fast right now. I promise a lot of this stuff has only happened over the last couple months or so, right? 2026 is going to be a crazy year for physical AI, and the pipelines are going to get very, very, very complex very fast, right? Today, we only are working at 100 different things right now, right? I mentioned data density, material density. We're going to look at deformable objects. We're going to look at things like modeling how I push through snow and if I slip on ice and all these kind of things in the future. So if your data pipeline isn't ready for this level of stuff today, it's only going to get worse in the future whenever the data gets even more complex for physical AI. Lastly, it's going to be data, not the models, that will define how far these physical AI models go, right? We're going to get new architectures. We're going to get new training parameters, all this stuff. It's going to be great. And I'm really excited for it, right? But it's not going to be based on the models that make your success the best. It's going to be based on the data, right? And how do I know this is true for sure? Because we're already training on internet scale data, right? You don't think Waymo doesn't have enough data, or Mobileye, or Wave, or Tesla. You don't think they have enough data today? They have years and years and years and petabytes and petabytes and I mean, like on the scale of hundreds of petabytes of data. And it's not enough. Like they still can't deploy self-driving today, right? And this is awesome. This is a great problem to have because it means that we're not just already going to lose. It doesn't mean that the race is over, right? It's going to be the engineers with the best ideas, the best tools, and the best data pipelines that are going to win. If you have a really great idea to find these edge cases, then employ it. Use Physical AI Workbench. I highly suggest, I mentioned this to everyone, right? I've coded Physical AI Workbench. I'm really proud of Physical AI Workbench. I would be nothing but more proud if you take it and build on top of it and make it completely your own and change all my lines of code. That's not the point, right? The point isn't my gusto or anything like that. It's to have you have the most success possible, right? And for the first time in such a long time, since really before LLMs, that we have this unique opportunity to pave this new road down this new area of AI we have no idea what the best answer is, right? Tesla doesn't use LiDAR. Is that wrong? I have no idea. Waymo uses 25 different sensors. Is that too much? I have no idea. No one has any idea, which makes this time so exciting, right? It's the best time to get into physical AI right now before the field really begins to heat up. So that way you can have the best results possible. And it's all going to start with having the best data pipelines and best data infrastructure. If you're not going to be able to rapidly experiment on synthetic data, reconstructions, or find scenes at a drop of a hat, then you're going to get left behind when it comes to storing all of this metadata, storing all this context, and mastering that physical to digital translation. So we're going to end here. I'm going to leave it for any questions. If anyone has anything, please drop it into the Q&A. I'll be doing my best here. I have some time here so I can stay online and kind of chat and answer any questions that we might have. But if you like what you saw here today, if you're interested, if this is something that you think can really help accelerate your organization's workflows for physical AI, or maybe you're just getting started, scan the QR here to help book a demo, and we're happy to bring Physical AI Workbench to even more context here for you. So I'm going to sit here for a second to make sure that everyone has a chance to scan. I'm going to drop the link here as well as please, 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 please funnel all of your questions into the Q&A. Like I mentioned, I have plenty of time to answer any questions and kind of clear up anything that might be still confusing for you. Okay, some great stuff coming in. So let's go for the first one here. After the data creation from Voxel51's end, do I have to set up and run NVIDIA's, for example, NuRec separately following their GitHub repo, or does Voxel51 have a one-line script in its pipeline to do the NuRec training and rendering? Great question. We didn't have enough time to cover it today. Voxel51 will cover that for you today. We have a bunch of scripts. One line is not entirely the truth today. It's more like a couple lines, but we do help spin it up for you. We help make sure that you have all the correct infrastructure and hardware and everything like that, and help work with that with you to help you with the reconstructions. There's a couple, different rendering options and reconstruction options that we can help walk you through as well. When it comes to the reconstruction today, it's very much an iterative process, right? It's going to depend on the overall quality. We've been mentioning so much about dataset quality. A lot of existing data is just not high quality. So, what type of training algorithm is the best for you? We have really, really great support from NVIDIA to help do this as well. So the very long answer to your question is yes, we absolutely have it all built in. One button click will run everything from data auditing all the way to reconstruction for you today. However, reconstruction is not an exact science. We will help iterate with you. We're happy to kind of put you into a POC or something like that until we and iterate there. The idea is to help you get the best workflow started and getting started and help build that together, right? And we're always very flexible with that. So great question. The answer is yes. We'll help you with the running of all the NuRec and Cosmos tools today. You do not have to build all that stuff yourself. We have a fun question here. Dan, what was the most fun problem you faced on with Physical AI Workbench? Well, there's a lot of unfun problems, so I'm glad you didn't ask that question. What was my most fun problem I worked on? It's probably going to be enrich. I think that's the most exciting part here. I've always loved puzzles, and I think coding in general is a puzzle and things like that. So this 9 out of 10 problem, this 8 out of 10 problem, right? How can we drop that number more and more and more to make it so even a new physical AI engineer or even the best is always getting their data set in the best representation possible, right? And so expanding that, we have a lot of really exciting features in the work for tracking algorithms and depth estimation and naive reconstructions and all this really great stuff that's coming in the works here that we're really, really excited to help work with for Physical AI Workbench. So solving the enrichment problem I think is one of where Physical AI Workbench stands out from a lot of the tools that exist out there, and expanding that enrich environment is something I'm really excited about doing in the future as well. One other friend asked, how easy is it to integrate data movement between Physical AI Workbench and GCP storage buckets? Great question. And let me see if I can get you a link here that's going to get you even better information on this. The correct answer here is it's going to be very easy because FiftyOne Enterprise makes it easy. Physical AI Workbench deploys inside of your environment, not a it's not SaaS. It's not like, on your platform. So if you are using Physical AI Workbench, it deploys into your GCP, Azure, or AWS instance. You can then, it's all logical. So there's no transferring of data. It's just pulling up and down, doing things like that. It all integrates with your EC2 and such like that, whatever VM, depending on what terminology you're working with. So great question. Everything is cloud native. Everything is cloud integrated. You're not going to have any headaches about moving data around things here, right? So good question, though.